Hello everyone, this is 𝐿𝐸𝐿 and I am back with the much awaited video, the book summary of designing data intensive applications. So if you have gone through my channel, there is a video series playlist basically in which there are 9 chapters covered, summary of the chapters of this book, designing data intensive applications. This is the book I was searching for. So this is a great book which is referred by a lot of people, and I already discussed the summary of 9 chapters, and there were a lot of comments on my socials as well as on the videos that when are you publishing those remaining 3 chapters, when you are doing that. Okay, so I thought let's complete that. Let's not keep that hanging. And I think it's been around 2 years, and a lot of things had happened since in between, and I was not able to get time or focus on this specifically. I completely left it out. But yeah, here we are. So I was saying that there a lot has been happened in the last 2 years. So I myself became author of a book, System Design on AWS. This is a O'Reilly book again, and it's among the top recommended books on O'Reilly platform, among the likes of designing data applications, designing data intensive applications. So it feels great to see this book among the most popular books on the internet. Okay, so check this book out if you haven't heard about it, or till now haven't explored it. You can check it out via O'Reilly free trial. You can read 2 sponsored chapters by Dragonfly, or you can read it via free trial, or you can reach out to me if something else can be arranged. But yeah, let's get started on the book summary of the chapter 10, which is batch processing. So here are my notes. Yeah, batch processing. So this batch processing is specifically around how can you process the data in bulk. Okay, batch means how instead of processing the data one by one, you take all the inputs all together. Okay, generally what you do is you take a request, you get a request on your server. Okay, you get a request on your server, and then you process that request, and then you return the response. Okay, now what we mean by batch processing is you get lot of requests all together. Okay, R1, R2, R3, lot of requests all together, you process them, and then you will return the result. Okay, so if this is how you can divide the systems as well, the type of systems. One is online system, which I just discussed, that you receive the request and then you process it as soon as it is received, and then you send a response. Then there are offline systems, which we are discussing today, which is batch processing systems, in which you take large amount of data, you process that, and then you generate the output. This can take time depending on how your job or how your system or how your application logic is configured, what kind of hardware you are using, and a lot of things. Okay, near real-time systems, this will be the chapter 11 which we will be discussing. So this is somewhere between online and offline systems, and there might be some acknowledgement response in first, and then you might get a response. So think it in this way, that you sent a request. Okay, you sent a request R1, this is my server, and then you send a response as acknowledgement ID something. Okay, that your request has been received, and then we are processing it. Okay, once this request is processed, then you send some kind of callbacks, that this is the response. Okay, so this is one of the way. Other way could be you suggest that caller that you retry again with this acknowledgement ID to check if the request has been processed or not. Okay, so these are the 2 general ways in which you check the response of these near real-time systems. Okay, now moving further, processing data via Unix tools. So this is one of the philosophy which we wanted to discuss first before we talk about the batch processing systems. And this is much discussed in the book as well, that how Unix philosophy is important in designing these big distributed systems as well. Okay, so let's take an example, how do you generally do some kind of processing. So let's say you have some kind of log file. Okay, not log file, log file, in which you have your what are the websites which are being accessed, or what are the web pages which are accessed on your website. So you have, let's say, your personal website, MsDeep Singh. This is my website, msdeepsingh.com. Okay, and if you try this hyperlink /books, you will find all the details of my book, System Design on AWS. So a lot of promotion, but yeah, you can check out all the details of the book there. So the idea here is how you will achieve those, like let's say you have that log file where you have this on this particular website msdeepsingh.com books, like what kind of web pages are accessed by the users. So what you want to do is you want to find top popular pages on your website. Okay, so how you will do it? You will read the log file, then you will do something this, like these are the different commands, Unix commands basically, which are piped together. Okay, so you run awk, you split each line into white spaces and output the seventh field in the like URL, like let's say this books, you will, so you skip all this and then you will get the books, so that is on the seventh place, let's say. Okay, then you do the sorting. Once that is done, you remove the duplicates. They're like on this log file, this books was accessed multiple times. Okay, so there are duplicates, right? And so you remove those duplicates. Then what you do is you sort by the number of time pages accessed, how many times those page was accessed, and once you've had that, you take the head of it. Head means the top values from this. Okay, so this is what you say, general processing, you can say. These commands are piped together. You might have seen that, like let's say you awk $7 and then you pipe that with some another command. Okay, so that one the output of one command is used as input of another command, and that's the same philosophy will be reading in the MapReduce as well. Like one job, like output of one job is used as input of another job. Okay, so that will be the idea. Now before we move further, let's discuss on sorting versus in-memory aggregation. What you can do. Okay, either you do that sorting or you do in-memory aggregation. So if dataset has lot of duplicates, it can fit into in-memory hash table. Okay, now why do I say this? I say this because in what you do in the hash table, basically you store the entries, right? So if there are a lot of duplicates, let's say my books. Okay, so you have accessed 5 times. Okay, then you have this about section that is accessed 10 times. Okay, so if there are a lot of duplicates, then you can store that in memory, because these entries are limited, only you are only increasing these counters. Great. But if the number of duplicates are less and if there are a lot of unique entries, then it will be hard, because the size of this hash table will be large and it will become hard to store all those values in memory, to fit in memory. If that is the case, then we can explore something called as SS tables and LSM trees, which is combination of in-memory and disk. I think we discussed this as part of this book as well. I am forgetting the chapter name, but yeah, we discussed that as part of this chapter as well. Okay, and this is heavily used by a lot of databases as well, where like for example Cassandra. Okay, these are the data structures which are used by a lot of databases for processing of data and then storing of data further. Okay, so Unix utility sort automatically splits data to disk and parallelizes sorting across multiple. So this is one of the, what you can say, fact for your knowledge, that how the Unix utility sort works. So if there is like a lot of data which is not fitting it into the memory, then it spills that data to the disk, and then also tries to parallelize the sorting across multiple CPU cores, if there are multiple CPU cores. If there are not, then it can't do anything. Now discussing the Unix philosophy. Okay, and this Unix philosophy, right, this is important. Like whenever you are designing any system, this is important that you have those basic ideas in place. Okay, like how you should approach a system design problem. Okay, so this Unix philosophy is much important. Like this is like discussed as part of this batch processing system, but this applies to any system which you design. Okay, maybe you are designing a simple payment system, so this will apply to there as well. So what is the first point? Make each program do one thing well. Okay, that there is a responsibility of a program, and that program is responsible to do that thing only. We are not bombarding that program to handle everything. No. Okay, so to do a new job, build afresh rather than complicate old programs by adding new features. Okay, so that's what we mean. If anything new comes in, we evaluate. Like if it tries to fit in, then definitely. If it doesn't, then we do not touch the old program. Expect the output of every program to become the input of another yet unknown program. Okay, don't clutter output with extraneous information, as in like if you are giving response to some API, right, you don't want to put too much information in there. We try to put and what we think is the required information, okay, what is useful information. Don't just keep on adding the information thinking that it might be useful in future, okay. If it is useful in future, then we will check again, okay, but right now if it's not, then we can skip it. Great. Now, design and build software, even operating systems, to be tried early, are ideally within weeks. Don't hesitate to throw away the clumsy parts and rebuild them. This is the general philosophy, that we try to build as early as possible and then create that feedback loop, so that if there is anything breaking, or you can fix that earlier, okay. Instead of waiting, or spending too much time in building that for perfect architecture. By the way, perfect architecture do not exist, which I keep on talking in my systems as videos. So the idea is that you build early, you take the feedback. If there is anything wrong, then you fix it. Okay, that's how you build the systems. Use tools in preference to unskilled help of lighten to lighten a programming task. Even if you have to detour build tools and expect to throw some of them out after you finished using them. Okay, this is just the idea that instead of doing everything on your own, you can use tools if they are available. And if you find out that tool is not usable, then you can just throw it, as in you can move on to some another tool. Or if none of the tool is working fine for you, then you can build one of your own, okay, and then share with people. So that's the great idea. uh, Basically, do not skip reinventing the wheel. Now, what is the limitation of Unix tools? Okay, they run on a single machine. Now, when we say there is the batch processing we are trying to do, that the data can be used, right? So the limitation with Unix tools is that they run on a single machine. You might have used a lot of commands yourself on Linux, Mac OS, or whatever utility you are using, whatever operating system you are using. I heavily used Ubuntu in my college. These days, Mac OS mostly, Mac OS. I really need to improve my pronunciation skills. But yeah, moving further. So we are trying to solve that limitation, that Unix tools are only running on a single machine. What we can do to solve that? The solution is MapReduce with distributed file system. So MapReduce is a framework basically which can work with distributed file system. When I say distributed file system, it basically means there are a lot of servers, okay, or lot of disks, okay, lot of disks, and your data is kept there. And somehow this MapReduce framework helps to gather the data from multiple places and then work accordingly. The data don't have to be present on a single machine. That's the idea. So how does this map reduce job works? What it does, take one or more inputs and produces one or more outputs. Simple. That's what every program does, by the way, that you are taking some kind of input. Once the processing is done, then you produce that output. Okay, so that's what MapReduce is also doing. Read and write files on distributed file system, HDFS is basically Hadoop distributed file system. Okay, so whatever program, or whatever logic you are doing, okay, so let's say in case of MapReduce, not let's say, this is how it works. So the idea is that you have your files present on the disk, okay, this is the input, and this MapReduce business logic mappers, basically they read the inputs from here, okay, they do that processing and all, okay, then they finally their output is saved to the disk again, okay. This is handled by reducer, this is mapper. Now, talking quickly about, we will talk more about MapReduce, how it works in some time, but let's talk quickly about HDFS, how, what's the design philosophy behind it. So this is based on shared nothing principle. So the idea is that there is no special hardware needed, okay, so it can run on your normal computes, whichever you have. So you don't have to buy a special hardware, that I want to run this HDFS, so I want to buy this particular hardware which is costly and all. This can run on commodity hardware, okay, and only thing we need is that the computers are connected with each other on the data center network, okay. That's one thing. Second thing is daemon runs on each node, exposing network service for other nodes to access file on that node, okay. So we say that when we say distributed file systems, we want to ensure that this server particularly should be able to access this file, all the files, right? Now if I say this, how will it access it? Okay, so there is a daemon, okay, daemon which runs on this every server, which makes sure that the networking port is open, or like that networking mechanism is in place, so that it can access the related file. Okay, so it's like a big distributed directory where it can directly access that file if needed. Name node, it keep tracks of file blocks on are stored on which node. Okay, so if a file has multiple blocks, or let's say the file has multiple replicas, where all are they kept? So this is kind of a master node, main node, primary node, whatever we call it in the terminology. So the idea of name node is that it keeps track of where the data is there. Okay, and for failures, the data is replicated on multiple nodes. So if there is a single file, single block, data block, that block is replicated depending on the replication factor. Generally it's 2, so that we have the data present at 3 nodes, but accordingly we can configure whatever is needed. Now let's quickly talk about MapReduce Job Execution. How will it work? As I said earlier, we will talk again in some time. So this is the time now on which we are talking about MapReduce Job Execution. So there are 2 components in MapReduce. One is mapper, and there is, so this map is basically mapper, and then reduce is the job of reducer. Okay, so there are 2 components, mapper and reducer. Okay, so what mapper does? Mapper takes the input record. Okay, so whatever is stored on the disk, it takes that input record. Okay, it extracts the key and value from that record. Okay, what is the key, what is the value? Okay, then it writes the output to the disk. Okay, so the idea in MapReduce is everything, whatever is done, like whatever processing is done, it is saved back to the disk. Okay, nothing is kept in memory. Okay, now the second components comes is MapReduce framework. Okay, in MapReduce framework, it takes the key value pair from the mapper. Okay, it takes that key value, whatever we have stored on the disk. Once that is done, it collects values belonging to the same key. So it's basically aggregating those values which belongs to the same key, and then it again writes the data to the HDFS. Okay, once that is done, the job of reducer comes in. What reducer does, it takes the collection of values and input. Okay, it produces the output, like whatever logic is there. Okay, what kind of evaluation we want to do. Let's say we want to count the number of values. Okay, so you have this key, and against this key you have 5 values, v1, v2, v3, v4, v5. Okay, so if you want to calculate the count, so the count will be 5. So this is handled by the reducer. Okay, once that is done, it is stored back to the HDFS, the file system. Okay, so this is how the MapReduce job execution works. General details: number of mappers equal to number of input files. Number of reducers is configured by the person executing the job, so you can configure that value. Framework use hash of the key to ensure all same keys end up on the same reducer, so that the processing is faster. Sorting is done in stages because large data size, similar to SS tables and LSM trees. If you know, like there are multiple sorting stages. Once that is done, let's say there are 10 blocks earlier. Okay, so once that is merged, then like from 10, let's say you converted it to 5. Okay, from 5 you converted it to 1, something of that sort. Okay, then the shuffle, mappers writes, this is mapper basically writes output the file. Schedule informs reducer work is done. Reducers connect to the mappers to download sorted key values for their partition and then do that processing. Now talking about the MapReduce workflows, there are multiple MapReduce jobs chained together in workflow. Output of one job is user input to another job, which we discussed earlier as well in case of Unix rules, that you try to use that pipe operator basically. Okay, to so that you can use input of one job as output to another, because there can be a lot of logic which could be in place, right? So keeping all that logic in a single place could be a burden, or like not feasible technically per se. Okay, so what you try to do is first to generate, like you process the input, you produce one kind of output, then you use that output to produce, like do another some kind of evaluation, then you produce another. So that lot of these jobs, I mean, lot of these logics can be chained together, C1, C2, or like T1, T2, where like mode of tasks are there, and then the final output can be again saved to HDFS, and the intermediate states are also saved to the HDFS. Okay, we can use a lot of open source tools or like softwares, or Yeah, softwares basically which you can use to like track the progress and all those things. So 𝐒𝐲𝐬𝐿 is one of the example, Airflow is another example. Now let's talk more into joins, like how the data joins work. Okay, so the first is reduce side joins and how you do the grouping. Okay, so the map reduce operation, right? It's now okay. Before MapReduce, let's talk about databases. If you want to make query faster, what you do? You try to index the data. Okay, you like in case of relational databases, you will create some sort of index on the columns which is not primary key, so that you can query that faster. Okay, in case of DynamoDB, you create GSI and LSIs. So the idea is that you are creating indexes on top of data which doesn't belong to the primary key. Now, in case of MapReduce, what MapReduce do? Okay, MapReduce do something similar to full table scan, which we know that is not it's not a good idea, right? But that's what the MapReduce is built for. We'll talk about some ideas later in some of the optimizations which were done in Spark and other frameworks, right? Flink for say, right? So that you avoid those intermediate states, and you also how like you achieve some sort of indexing kind of functionality, so that you don't have to read the entire data. Basically, if you don't need the data, then you don't read it. Okay, but coming back to MapReduce, MapReduce job is similar to full scale table, so it will read the entire data set. Let's take one example. Okay, so let's say you have two data sets. The first data set stores log entries for the user activity. Okay, great. Another thing is user info table. So in case of first one, you have a user, and then you have the user ID, and then like what action was taken by this particular user. Okay, but in this case of this particular database or like files, you don't know what this 101 mean. So I want to get more details, like let's say what's the name, MsDeep14, what's the age. Okay, so there are multiple users, 101, 102, 105. Okay, MsDeep14, this is my LinkedIn handle. Mandeep Singh, this is my real name. MsDeep Singh, this is my YouTube channel name. So if you haven't subscribed to the channel yet, consider subscribing. You will learn a lot of things, such as this great video book summary for designing data intensive applications. Okay, so let's say you have this data at two places. Now you want to club that data because you want to know like this 101, like who clicked that button and what's the age, so that you can do other operations. Let's say I want to access like that particular age group is clicking this button more. Okay, so you can target for let's say advertising or like other use cases which you can think of. So the idea is for collecting data, infer who is user from the log entries, and then you access the log entry one by one and then call the database. Okay, so what you are doing is you are doing that one by one, and then you are calling the database that who this user is. So you access first entry, then you call this database who is 101, and 101 is MsDeep14. Okay, who is this 105? 105 is MsDeep Singh. But this is not very efficient. Okay, what you are trying to do here is you are reading that file one by one and then trying to access that database. Okay, you are making that network call to the database. Okay, and this log file can be really huge. So can we do some sort of caching? Can we do some sort of caching if we want to avoid that database call? The general idea that comes to our mind is, can you do the caching? So can we do it? So what we do is we leverage local cache. When I say local cache, if this database is not that big, what you can do is you can take the dump of this database on the particular data. I mean, where on the HDFS file system, basically where this MapReduce job is running. Okay, so this is a better approach. This is particularly a better approach if you can take the dump of that entire database. And if that's not possible, what you can do is at least keep a local cache for some time. Okay, if this is not feasible, that this data set is very huge, so keeping that dump of this database can be a big bottleneck. Okay, so what you can do is, like whenever this entry comes in, you can at least keep some sort of local cache on that node, so that if that same user ID comes again, then you can infer from that local cache entry. Okay, and if it's not present in the local cache entry, then you make that network call. So depending on the use case, this can be done. Second is short merge joins. Okay, so now we talk about, if it say like how does MapReduce execution works. So let's say you have two mappers, mapper1 and mapper2. So mapper1 extract user ID, which is key. Okay, it figures out the activity details, which is value from the user activity log entries. And what does mapper2 do? It extracts the user ID key, and then it extracts the user details from the user database. Okay, so we had two databases, user this log entries database, and then the second one is user table database. So mapper1 is responsible to extract the data from first one, and then the mapper2 is responsible to extract the data from second one. Now what's the output? Okay, so the MapReduce framework partitions mapper output by key and then sort key value pair. Okay, with me, all records, user activity and user database with same user ID become adjacents. Why? Because you have that mapper is making sure that if the same user ID comes again, it is kept near to that, like whatever entry was there already. Okay, now this is used as reducer input. Reducers can process all records for a user ID in one go. Why? Because they are adjacent to each other. Keeps only one user record in memory at a time, and there are no network calls needed. Okay, when I say network calls, basically if there are on multiple files or like so that sort of thing is not needed. Called short, this is basically called short merge join. Okay, why? Mapper output sorted by key, reducers merge the sorted list of records from both sides of join. Okay, so we call this as sort merge join. Okay, and this is also called as reduce side joins, because the join work is done by the reducer, so we also call it as reduce side joins. Reduce side joins. The related data is at the same place, helpfully achieving group by kind of operations as well. Okay, so since we have ensured that all the related data is at the same place, then we can also achieve the group by operations. Example, counting page views. Okay, so those count aggregation operations which you do in the relational databases, which this can be done easily because these record entries are adjacent to each other, so it will be much easier to do that. What about celebrity user? Okay, so this is the popular problem, right? This is a popular problem. You said what you said? You said that all the entries are adjacent to each other. Okay, for that particular user. But what if it's a celebrity user? Then there will be lot of entries. So what you will do? Okay, in that case, it might not be possible for a single reducer to handle everything. Okay, because that celebrity has lot of entries. So what you try to do, one reducer doing a lot of work as compared to others, this will create a hot partitions basically, right? Skewed or hot participant, hot spots for that celebrity user. There are also called linchpin objects. This celebrity product, not product, celebrity user is called also this, like the entries are basically also called as linchpin objects. Okay, and this can take lot of time to MapReduce for the task completion, because other tasks are waiting for this celebrity user to complete. So can we do some sort of parallelization? So instead, mappers send the hotkey to random reducers based on some hash, and then multiple reducers can work together to achieve the output what we are seeking. So we are trying to parallelize that data, and then we are getting the output. Second type is map side joins. So we discussed reduce side joins. Now second type is map side joins. Mapper reads the file from HDFS and then write back to HDFS. So there is no reducers or sorting involved. Okay, so mapper is basically handling everything. Mapper is reading the file from HDFS, is doing some processing, and then it is writing back to the HDFS. There are multiple types. First is broadcast hash joins. This is helpful if there is one large data set and another one is smaller data set. Okay, which can fit into a memory of each mapper which is there, which is reading that file. Okay, so a smaller data set is broadcasted to all mappers, and then it can be easily joined together, can be handled by mapper. In pig, it is called replicator join. In case of hive, it is called map join. Second type is partitioned hash join. Now in this one, inputs to map side join are partitioned in same way. Okay, so let's say if there is a user ID, so you will partition that user ID into 10 partitions. Okay, so for every user ID, like whatever the user ID is, you will know that there will be 10 partitions for that particular user ID. Okay, in case of hive, we call it bucketed map joins. The third type is map side merge joins. So it is partitioned in same way and sorted based on some key. Okay, so you have that it is like a mix of partitioned hash join plus they are sorted based on some same key. Okay, so this is the third type. Now this is the all the operations we have discussed, like whatever processing we have done, with the MapReduce. Now let's discuss what you will do with that output. Okay, so output of batch workflows, result of data processing, what you are trying to do. So there are some of the use cases. There can be a lot of use cases like recommendation system. I took that example. Okay, so there are multiple examples. One example is that building search indexes. So you have a lot of data. Okay, you have a lot of data, and from that lot of data you create those search indexes. Okay, in Lucene or Elasticsearch or open source or anything which you are using. You read those files and then you dump those files that for that particular entry, or like if the user is searching with something, how can you locate that file? So that's where that search index comes in picture. Okay, this is one of the example. You can build key value stores as a batch process output. What you can do, you can create spam filters, anomaly detection, recommendation systems. These are some of the use cases. The output saved such that it can be queried by some key. So as I said, right, key value, you can try to store them based on some, let's say, user ID. Okay, now what I want to do is, let's take this example. For this particular user ID, I want to know what are the suggested connections. Okay, what users I can suggest to this user that try to connect with those users. These are mutual or like on interest or like other factors, locations or anything. Depending on that, you can suggest those users. So what you did that MapReduce execution, you stored that output. The output contains key value pairs for that particular user ID. These are the list of connections which can be suggested. You suggest those, and this is how it works. Okay, kind of recommendation system. Now let's compare this Hadoop to distributed databases. There are a lot of distributed databases, as in not running on a single machine but on multiple machines. First thing is diversity of storage. Now, if we talk about any databases are kind of structured. Okay, when I say structured, like I am discussing both non-relational and relational databases. Okay, there is some sort of structure that you specify some sort of primary key. Okay, like the DynamoDB is non-relational databases per se, right? But you still specify that partition key, short key, and like how you are, and then you can have random columns in place. Okay, in case of relational, that is more structured in place. Okay, so in case of relational databases, you specify all the columns and then the types, what are the types of those columns. Okay, so diversity of storage. Databases are more structured. Hadoop works on files, so can be written using any data model or encoding. You are not bounded by that. Okay, you can dump anything to files and later figure out how to process it. Don't have to worry about the schema design in case of Hadoop file system. Diversity of processing models. So MapReduce allows to run your own code on large data sets and don't depend on database software. Okay, so what MapReduce is basically a framework, right? And you can write your own code in Mapper and Reducer. Okay, so you can do all sort of things, whatever is needed. Okay, you don't have that dependency, like how that particular database is working, or like there is some structure which you have to follow, or like if you follow this kind of query pattern or this kind of structure, then your database operations will be more faster. Okay, so you don't have that kind of dependency in case of Hadoop. Okay, so diversity of processing models. You can build tools on top of MapReduce. Whatever it is, let's say pig, hive. Okay, all these are built on top of Hadoop to make your life easier, so that you don't have to write those mappers and reducer again and again. Designing for frequent faults. Okay, so in case of MapReduce, what we are doing is like the output of one operation, okay, is saved to the HDFS. Okay, and then it is accessed again. Okay, so if something fails as something fails in stage 2 or something fails in stage 3, I have those outputs stored on my file. Okay, so I don't have to execute that stage 1 and stage 2 again. I can directly start the stage 3 because I have the output of stage 2 on my file system. Okay, so if task is aborted, it can be retried, and this also enables resource utilization. And in case of in the book Designing Data Intensive Application, this is discussed like why this is important. Okay, why this is important. It is not always there that we want this feature to ensure there is no hardware failure. Okay, there might be no hardware failure. Okay, but the main idea is, can I preemptively stop this execution? Okay, let's say there is some more priority code and I have limited resources. If I more priority jobs comes in, then I want to execute that job first. Okay, if I want to do it, then I have to close this task. So you execute that more priority task, and then once those tasks are done, then you again start this less priority task, and then it can start from wherever it was left off. So that's why we need those fault handling. It is not just for hardware failures, but there is another reason beyond MapReduce. Okay, so there are some problems with MapReduce we will discuss, and then like what are the solutions to it. Okay, so writing MapReduce jobs from scratch is hard and time consuming. Why? Because I said it gives you a lot of flexibility that you can write your own mapper, you can write your own reducer. Okay, it gives you a lot of flexibility. You can write whatever you want. Can write your logic like however you want to process your data. Okay, but this also brings in churn that you have to do lot of work. Okay, you have to do that lot of work, and it's time consuming, it requires expertise and all those things. So let's discuss few of the things how you can improve it. First thing is materialization of intermediate states. Okay, now when I say intermediate states, I said that there can be chain of executions, right? We said that we can use UZ or airflow to see that like what is happening in these stages. But the main idea of MapReduce was that whatever intermediate state is there, okay, in a single job as well, mapper does something, it writes the data to HDFS. Okay, once the complete job is completed, like one task is completed, the data is written to HDFS, then it is read again. Okay, so this is output of one job acts as input to another job. Writing out this intermediate state of files is called materialization. Okay, now what are the issues if we are doing this? We are storing these intermediate states because it offers great fault tolerance and all those things, but there are some issues as well. What are the issues? MapReduce job can only start when preceding job is completed. It requires more execution time. The next stage can only start if the previous stage is completed. So if there is a dependency, then it has to wait for that data to be written and then it can access it from there. Intermediate files are replicated on HDFS. Now these are kind of temporary files, right? You might not want to replicate those files on multiple nodes. This is a kind of overkill scenario. Okay, so to fix these, there are multiple data flow engines such as Spark, Taze, Flink, and it can handle the entire workflow as one job instead of breaking into multiple sub jobs. Okay, and in this case, sorting is done only when it's needed. So these are some of the improvements which came in later. Okay, in these frameworks, so sorting is done only when needed. No necessary map task, unnecessary map task. Locality as an optimization is task consumer producing on same machine, so data transfer or network can be avoided. Okay, so let's say you know that the second stage or like the part of that operator in case of Spark, the data will be accessed, right? So you will save the output on that same machine where it will be accessed next. So there will be no network calls needed. Can write to local disk or memory instead of HDFS. So instead of HDFS, which ensures that the data has to be replicated on multiple nodes, what you can try to do is you can use local disk or memory to write the data, and in this case there is no replication needed. Okay, not that scenario. You can also configure replication factor as well. Fault tolerance. Okay, so like you said that you will not leverage HDFS per se. Okay, but what about fault tolerance? We said that fault tolerance is pretty important, right? And it's there. And if you're talk about distributed systems, the fault tolerance mechanism should be there. Okay, so MapReduce writes intermediate files to state HDFS tasks can be restarted on one machine on failure. This can be handled. We discussed that. Spark don't write intermediate states to HDFS. So if machine is lost, data is recomputed. So instead of saying that I will what you say instead of saying that I will read the data from HDFS, I will recompute the data of the stage 2. Okay, all you have to ensure is that it's an idempotent kind of job. Okay, so if you want to recompute again from that stage, the output should be same. The output should not change on second execution. So that's the only thing we have to ensure. If we can do that, then we can say that even if the data is lost, I will re-evaluate the data, recompute the data by running that stage again. Great. For this, it keeps the track of how data was computed. Use resilient distributed data set RDD. Okay, this is one of the thing which is used. The recomputed data should be same. If not, then entire job should be rerun. If computation is CPU intensive, materialization of entry steps is cheaper, not cheaper. Chapter. Okay, so if you, let's say the recomputation is very CPU intensive, so instead of doing that, what you can do is in those kind of intermediate states, what you can do, you can write the data to the file system. Okay, instead of depending on that recomputation. Okay, so you can do mix of things so that you take best of both worlds. Materialization as compared to MapReduce, write only needed intermediate states and not all. Okay, this is what we discussed. You can decide based on, like, if it's a CPU intensive, then you can decide to write that intermediate state. If it's not, then you can decide to recompute if needed. high level APIs and languages. There are a lot of things which are developed on those systems. Okay, so writing MapReduce job is laborious task, which we discussed this. You need expertise, you need time to write those mappers and reducers. Okay, it gives flexibility, but it also has its own bottlenecks. So there are a lot of open source softwares. There are a lot of tools which are provided by private companies which are not open source. Some of the examples are Hive and Pig, which are open source tools which can be used. Now, writing code requires more expertise and work. Okay, so it provides declarative interfaces and then it makes it easy. Okay, add internal execution engine can also decide the way to execute for faster task completion. Spark, Hive and Flink have cost based query optimize. So these are all the things which are there. Okay, and this we already discussed, right? There are some bottlenecks in MapReduce, and this is what all these tools try to solve. And this I mentioned this one thing, right? Instead of reading that entire data set, we used indexes in case of relational databases, but MapReduce is kind of full table scan. Okay, so in here, in case of Spark and all, instead of reading the entire data record from this, it can also read only required fields. Okay, so yeah, I mean, this is all about the review of chapter 10, summary of chapter 10. For more details like in-depth analysis and all, like if you want to read it by your own, you can definitely check out the book. I think it's also freely available online by SkylarDB. I will try to find that link and share with you in the video description. If you haven't subscribed to the channel MsDeep Singh, consider subscribing. And if you haven't checked out the book Systems Design on AWS, check it out. It's a great resource to learn system design, starting from the fundamentals to building large scale systems. So check it out. We will meet again in the next video, next summary video, or any general system architecture discussions. Till then, stay safe. Tata. Bye bye.